Well, last time we talked a little bit about the history of the formation of the periodic table, and I understand that's not the most exciting thing we're going to do. But now we're going to take a closer look at the actual periodic table that we use today and see how we classify some of the elements and why the periodic table looks the way it does because of the periodic trends that are involved with the elements. So first, take a good look at the periodic table of the elements. And there's some things I'll write up here that we'll talk about as we go through the process. First, I want to come over here and I want to draw a little staircase right here through these elements for a reason. Because there are three main categories, and you're going to see the definitions of these words in just a little while. See that staircase I just drew? The elements to the left are all called metals. You've heard of metals, obviously, and we're going to put the actual definition of metals up there on the next screen. But the metals are all these elements to the left, let's move that out of the way, except for hydrogen. To the right of that staircase, I'm going to write the word non-metals here, and then include hydrogen as well. Now you see the nonmetals up here are colored in blue, but you have to realize this group in purple and this group in pink, they're also nonmetals, although the color code might make that look a little different. Now you look at all these elements here that touch the staircase. These, I'm trying to look for a good spot, I'll just write it up here. These are called metalloids, and again we're going to define those a little bit on the next page. During this set of notes, we're also going to talk about periods, which are the rows that go across, and groups or families. These are the columns that go down. So this period number 3 and this group 2, which is also known as 2A, those numbers have some meaning, and we'll talk about those as we go through this session. Are we ready? And here we go. Types of elements. Find even more so on pages 80 and 81. You saw that I drew that staircase, and the atoms to the left, except for hydrogen, we called metals. Now you know a lot of metals already. Iron, copper, zinc, cobalt, magnesium, gold, and silver. These are all kinds of metals. And the definition of a metal is simply an element whose atoms give away electrons, namely those valence electrons that we've talked about a few times before. It's the valence electrons that cause atoms to combine. And again, before long, we're going to see how those atoms start to combine. To the right side of that staircase that I drew, those elements plus hydrogen, those are all called nonmetals. These are the elements whose atoms will take those electrons that the metals like to give away. And those are the reasons why atoms will bond together, the give and the take, and even the sharing of those valence electrons. Now, remember I kind of pointed to those elements that are right along that staircase I drew? Those are the ones called the metalloids. And those could act either as metals and give away valence electrons, or as nonmetals and add on those valence electrons. And usually, especially for an element like boron, number 5, the hotter the element is, the more metallic or likely that a metalloid will give away electrons. And the cooler the temperature of the atom, then the more likely to be nonmetallic and add on those electrons. And again, these are found touching that staircase that you're going to see on many periodic tables that you encounter. Those make good semiconductors. Now, where do we find semiconductors? These, try that again, drawing tool didn't quite come on. These are the little chips inside computers and phones and electronic devices that control just how much electricity goes into the device. Let a little bit of electricity flow through by letting a few electrons at a time flow through so we don't burn out our devices. Silicon and germanium especially, those you will see on the periodic table make excellent semiconductors because they're very good metalloids. Ready? All right, what about metals now? about 3/4 of the elements are metals. Now, if you look at a periodic table, or think of the one that I had on the screen a moment ago, most of those elements are to the left. And remember those two bottom rows as well? Those are also metals. We'll talk more about those in a little while. But almost 3/4 of the elements are metals, about 75%. That means about 3/4 of the elements like to give away their valence electrons. Most metals are very hard, very strong, and very dense. Okay, just what you mean by hard and strong and dense, well, they're difficult to break apart, although some are softer than others. Sodium is actually a fairly soft metal that can be cut fairly easily with a sharp knife. Gold, pure gold, that's actually much softer than many people believe. Dense means there's a whole lot of material in a small amount of space, and so metals are very likely to sink in most fluids. Okay. Metals have few valence electrons. In fact, most metals have either 1 or 2 valence electrons, but a few have 3. And we're talking about group 13 and 3A, the group that has boron on the top, and it's right where that staircase is that I showed you. So if you have a periodic table handy, look at that while we talk about these. Of course, if you're in class, you're going to see that on the wall as well. The transition metals, a big bunch in the middle. Most of those have 2 valence electrons, a few of those have only 1. But these are your characteristics of metals. Ready? 92 of the elements occur naturally, and 26 of them are purely synthetic. There are 2 elements that can be both natural and synthetic, and those would be technetium, element number 43, and promethium, element number 61. Of the 118 known elements, or the 92 natural elements, 79 of those are solids at room temperature. Nice and solid, like you hear the knocking there. 11 of them are gases at room temperature. And let's just remember what these elements are. Hydrogen, helium, neon, oxygen, fluorine. Let's try that again, I goofed. Hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. These are your 11 gases at room temperature. There are only 2 elements that are liquid at room temperature. Hg is element number 80, mercury, right here. That's what is in the thermometers. You know, we have electronic thermometers now, but the old-fashioned thermometers, you get sick, mom puts that in your mouth, or the nurse will do that to take your temperature. Of course, we have electronic ones now, but the mercury is the liquid metal that will expand when warmer and contract when cooler. And bromine is found in ocean water. That's the only non-metal that is a liquid at room temperature. Now, there you see the 92 natural elements, 79 solids, 11 gases, and 2 liquids. Ready? The word monatomic means one atom. This means this atom can exist by itself, and that's going to be most of the elements, such as sodium, potassium, calcium, scandium, vanadium. You can see those that will exist as a single atom. So that, again, that just means that we're going to have something like calcium that we can write as just the symbol Ca, or iron as just the symbol Fe, or even potassium. But you see there are 7 that are so reactive they cannot exist as single atoms. They have to exist as pairs, and here they are. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These elements, their atoms are so reactive that they will not exist by themselves. They're going to find someone else to hook up with. There's no what if they don't. They are going to. If they can't find someone else to hook up with, they'll find another one of their own. That's why you're going to have 2 hydrogens together, or you'll have 2 nitrogens together. Maybe on someone's oxygen tank, you see the symbol O2 because oxygen is one of these diatomics. The time will come where I'll make sure you memorize these. But right now you can just look And I'll remind you of these again and again, and when we're looking at a periodic table together, I'll show you how we can make that known and a lot easier to recognize. Valence electrons. Again, these are the party animals. Valence electrons, there's your definition again, the electrons that are on the outside energy level of the atom. I know I said this a few times already, but it's the valence electrons that cause atoms to have their chemical properties and to combine with other atoms. In fact, chemical properties includes how the atoms combine with each other. The valence electrons do that. On a very rare occasion, electrons on the next energy level that's not valence could be involved, but almost all the time it's the valence electrons that cause atoms to combine. And I want you to know this number 8, which is why I highlighted this in red. This is a magic number right here, because almost every element, with a few exceptions, they're trying to get 8 valence electrons. When we talk about elements combining in our next chapter, then we'll see that a little bit more clearly. And I'll tell you about the exceptions at that point as well. But almost all elements are trying to get 8 valence electrons. Why the number is 8, I really don't know. God knows exactly what he's doing. But you look at the top of a group that has an A, 1A, 2A, 3A through 8A, that's going to tell you how many valence electrons are in that group. So if you look down group 7A, where the top element is fluorine, followed by chlorine, and then bromine, iodine, and astatine. That's down group 7A. That makes it very easy to identify that all of these elements in this group have 7 valence electrons. And that's going to work for all the atoms in a group number with an A. The only exception would be helium, which is in group 8A, because helium has only 1 energy level. And you may remember from a previous set of notes, that first energy level can never pass 2 electrons. More about that in a little bit. And there are 2 of the exceptions to helium and hydrogen of getting to their 8 valence electrons. I just started to mention that with helium, and there are actually 3 more. But remember, hydrogen has only 1 energy level and really only 1 electron. Helium has 1 energy level and 2 total electrons, and they're valence. And we cannot put a 3rd electron on that energy level. Even when hydrogen combines, let's say hydrogen combines with oxygen to make water, hydrogen might get that 2nd electron there, but can never go to 3. Helium is a noble gas. Helium is stable and will not combine easily with other atoms unless forced to. Therefore, helium's not trying to get any more valence electrons. But down that last group, once you get underneath helium, you have neon and argon, and go straight on down that group. You're looking at krypton, xenon, and radon. All of those have 8 valence electrons once you get here to neon and go down. Helium, though, just the 2 valence electrons, but neon is going to have all 8 of those, and so will all the other elements in that group. Now, there are a couple more exceptions that I'll tell you about another time where they're not trying to get all the way up to 8. There are only 3 more. Ready? Reminder that hydrogen and helium have only the 1 energy level, and the maximum on the first energy level is 2 electrons. So hydrogen and helium are 2 of the exceptions for atoms trying to get 8 valence electrons. And I said this a few times, now you see it on the screen. The valence electrons cause atoms to react with other atoms. They can be shared or transferred, which is really what the next chapter is all about. Ready? Now let's look at some of the element families. Showed you a little while ago that vertical groups going down, they're called groups or families, all the columns. And it is the number that's going to help us determine how many valence electrons, especially in the A numbered groups, that each element in that group is going to have. Atoms in the same family going down have the same number of valence electrons. Atoms in the same family react similarly with other elements. So look down group 2A, magnesium and calcium, they're going to have similar reactions with other elements such as oxygen and sulfur. They'll do pretty much the same things. Maybe one will be a little more rigorous than another one will be, but they're going to do kind of the same types of combinations. Your vertical columns are called either groups or families. Ready? Now let's look at each group as we go across from the left to the right of the periodic table. Group 1 is over here on the left. It's also called 1A. So if you're looking at a periodic table, you can see what I'm talking about. This is called the alkali metal group. Now notice that hydrogen is at the top of that group, but hydrogen is not a metal. Hydrogen is placed into group 1A, however, because hydrogen has one valence electron. And with these metals, that one electron is held very, very loosely on that outer energy level. Even more loosely or less tightly as we go down, lithium, sodium, potassium, rubidium, cesium, then that electron gets even more and more and more ready to jump off that atom and combine with something else. That one electron just cannot wait to leave that atom and jump onto some other atom. And that's why these are extremely reactive, and they're never found alone. You're not going to find pure sodium very often. Sodium's going to hook up with something like chlorine. Tell you why in a little bit. Potassium's very easily going to hook up with something like bromine. Tell you why in a little bit. Remember that magic number of 8. Now these metals are highly combustible if put in water. Take a piece of sodium, drop that in water, it's dangerous, so I'm just saying it. Wait just a little bit. You might start to see a flame and then an explosion. So imagine a larger chunk of sodium in a larger amount of water, and there are videos on YouTube you can search and see that. And then as you go down that group, potassium, rubidium, and cesium, drop those into water and the explosions get even more and more violent and vigorous. They all combust or even explode when put into water. Water has oxygen, and when those water molecules are broken apart by the energy released of the reaction, that's what causes the explosion, and also the hydrogen that's involved with that water molecule being separated as well. The hydrogen is really what explodes, but the oxygen helps the reaction take place. Now it sounds weird, but these metals can be very dangerous when by themselves, but they're also essential parts of our diet. We have to have the right amounts of sodium and potassium in our diet. If we have too much or too little, we can get some real health issues, especially sodium. Too much sodium in our diet, salt, that can cause some heart problems and so forth. My father, he died because he had too much potassium in his blood. Well, he had to cut back on potassium-rich foods such as bananas. But of course, he also smoked for over 30 years, and that didn't help either. So watch your smoking. Ready? The alkaline earth metals. This is group 2A. So at the top, we see beryllium. And as we go down, we see magnesium, calcium, strontium, barium, and radium. These have 2 valence electrons. So again, look at the number in front of the A. The 2 in front of the A tells us that these elements have 2 valence electrons. Those are found in most minerals, and minerals are found maybe in the Earth's crust. They're also good nutrients in our diet. Our bones need calcium. Our teeth need calcium as well. They give us a lot of strength in our bones. Okay, magnesium may also be found to help fight heartburn and too much acid in the stomach. So many of these elements are also nutrients in our body. Calcium is found in mortar to help building materials such as the walls that make up this classroom, mortar, plaster, stucco, and glass, because calcium is a very hard, rigid, almost impossible metal to cut with a knife. Extremely strong, and that's why calcium is used in some of these building materials. And we want to drink milk and have cheese and have dairy products because those things have a lot of calcium in them to give us strong bones and teeth. Ready? Oh, I forgot about barium and beryllium. Barium, Ba, and beryllium used in medical x-rays. I've had x-rays where I've had to drink solutions of barium and beryllium. If you've ever tasted chalk, then you know what these two things taste like. But those help physicians take x-rays of things that weren't my bones so they could figure out the kind of health issues I have, and now I'm able to be treated for them. But these are the alkaline earth metals, group 2, also known as 2A. Ready? Okay. The transition metals. These are the ones you're going to find about 4 rows in groups 3 through 12 across the middle of the periodic table. Most of these have 1 or 2 valence electrons. These metals will combine with other atoms, but not quite as easily as the 1A and the 2A, the alkalis and the alkaline earth metals. Those two groups react very easily with elements on the right side of the chart. It turns out that the further you go to the left and to the right on the periodic table, except for the far right, those elements tend to react very easily. But near the middle of the chart, those elements react less and less easily. Copper is used in wiring. Copper is also used in many pipes. Mercury, I mentioned in the thermometer before, and mercury is found in many seafood products. People like to eat seafood, they're eating a lot of mercury, but mercury can also be poisonous. Mercury is used in fluorescent lighting as well. So if you break a thermometer, you break a fluorescent light, you want to put some gloves on before trying to clean up the mess. Make sure that you don't get that into your skin. It's not deadly, but it can make you feel pretty weird for a while. Now, most transition metals are not used in their pure forms, but they're melted down and then frozen into what's really a mixture of metals called an alloy. So much of your gold jewelry isn't pure gold. It's gold mixed in maybe with some copper to help give it a little bit of strength, even a little bit of zinc and calcium. Our coins are made of zinc and copper and a little bit of nickel. In fact, the coin nickel used to be made mostly of nickel, but then copper and zinc are less expensive to use. So that's what our coins are made of now. Sterling silver is copper and silver. Silver is element 47, Ag. Copper is element 29, and they're actually in the same group over on the right side of the transition metals, group 1b, and they both have 1 valence electron, and gold has 1 valence electron and is listed right underneath copper and silver. So in group 1b, you're going to see copper, then silver, then gold, 1 valence electron, and that group going straight down. And with a couple more exceptions, the other transition metals all have 2 valence electrons. Steel, something you're very familiar with. In fact, the seats and the legs of the stools you're sitting on, and in the other classrooms, the metal chairs, they're made of steel, which is iron and carbon. And how can I tell? Because iron's magnetic. If I stick a magnet to one of those chairs, that chair is most likely made of steel, but carbon helps give that a little bit of strength as well. Ready? All right, some of the other families, they don't have some fancy names like alkalis and alkaline earth metals, and that's because in 3A, 4A, 5A, and 6A, there's a mixture of the 3 different kinds of elements that we have. Boron family is group 13, also known as group 3A. And everyone in this group has 3 valence electrons. And this group consists of boron at the top, then you have aluminum, gallium, indium, and thallium straight on down. So in group 13, or group 3A, the boron family, notice boron is at the top, so that's the name of the family. We have a metalloid, and then we have some metals. Move over one to the right to the carbon family, group 14, or 4A, 4 valence electrons. So again, 3A, 3 valence electrons, 4A, 4 valence electrons. And even if you look at the 13 and 14, 1, 3, 3 valence, 1, 4, 4 valence. So no matter which pair of numbers that you use, 1 through 18 or the 1A through 8A, you can figure out the number of valence electrons. Carbon family consists of carbon at the top, followed by silicon and germanium. Now, carbon's a non-metal. Silicon and germanium are metalloids. Then tin and lead, those are metals. So there's a mixture, and that's why these don't have big fancy names like alkaline earth metals. Ready? Next group, the nitrogen family, group 15 or group 5A. Oh, I see a mistake. I'm going to pause and correct that. Okay, you know what? Mistakes happen. It shows that we're all human and we all tend to make the mistakes, and I do too. So I made the mistake here and I made the correction. 5A has 5 valence electrons. And in this nitrogen family, nitrogen, of course, at the top, then we have phosphorus underneath. Those are both nonmetals. Then we have a couple of metalloids, arsenic and antimony. And then underneath that, we have bismuth, which is a metal. Now think of Pepto-Bismol you might take if you have an upset stomach. Bismuth, the main ingredient in there, helps neutralize some stomach acids. An oxygen family, group 16, 6A, oxygen at the top. Then we have sulfur and selenium, nonmetals. Then we have the metalloid, a toxic, poisonous one called tellurium. And then we have our first radioactive metal, 84 and above, called polonium. But again, technetium is element 43, and that's also radioactive. But the big group of radioactive elements begins with number 84, polonium. The oxygen family, 6A or 16, 6 valence electrons. Ready? Okay, then we get to group 7A or 17, and we call that the halogen group. And here I'm going to remind you of that magic number of 8. Sometimes that drawing tool doesn't quite go. Now remember, group 1A has 1 valence electron. This group right here has 7 valence electrons, the halogens. What does 1 plus 7 equal? That equals 8. So this will help us see a little bit more easily why sodium, which is in group 1A with 1 valence electron, hooks up with chlorine, which is a halogen, group 7A, 7 valence electrons. This 1 plus these 7, that's a total of 8 valence electrons. And that's where we get sodium chloride, or the table salt that we put on our French fries. We look for groups whose valence electron numbers add up to 8, and we can see how certain atoms will fit together very well. Now remember the word diatomic I showed you a little while ago. There are 7 of those atoms. Well, 4 of them are in the halogen group because they're so very reactive. Because they have 7 valence electrons, they need 1 more, and they're all just looking around for 1 more valence electron. Please, someone give me an electron. And then you got the alkali metal saying, I have this 1 electron to give away. Please, somebody take this 1 electron. And again, you can see why alkalis and halogens love to hook up with each other. But if these guys can't find an alkali to hook up with, they'll combine with another one of their own. The next chapter will show us how that happens. The lower the atomic number in this group, that means the top of the chart, fluorine and chlorine. They're lighter in color, and as we go down the column here into bromine and iodine and astatine, then they're going to get darker and darker in the color. Astatine is more of a solid. Remember, iodine is a solid. Bromine is the only liquid nonmetal at room temperature. Fluorine and chlorine are both gases. Now, chlorine is a very deadly gas in its pure form. But when combined with sodium, makes something we eat. And I mentioned that before. The lower atomic numbers at the top, those are gases. Again, that's fluorine and chlorine. Then we get to the liquid, bromine. And then we get to iodine and astatine. Those are solids. Talking about the atomic numbers, and the atomic numbers go higher when we go down the group. Now these are okay in small amounts, but they're very dangerous in large amounts. I mentioned chlorine gas, very deadly. And I always get someone ask, well, what about the chlorine that's in the swimming pool? Which is a perfectly legitimate, fair question. The chlorine that's in the swimming pool is in liquid state, so much, much less energetic and dissolved in a comparatively tremendous amount of water. So that's dissipated, it's nowhere near as strong, but it's going to help kill the germs in the water. But unless you swallow a bunch of it, it's not going to harm us. Ready? Chlorine, fluorine, and iodine are also needed in the body because all three of these help kill germs. We use fluorine where? In the toothpaste. We have monosodium fluorophosphate or sodium fluoride in the toothpaste we brush our teeth with. We kill the bacteria. The bacteria love to eat the sugar that gets left over on our teeth. And when they're done with the sugar, they'll start eating away at the tooth itself. But chlorine and iodine also help kill germs in the body. Now, ready? Okay. The last group to the right is called noble gases. This is a very, very, very stable. So if I had the periodic table up here, it'd be to the far right. And you'll see that again in just a little bit. Group 18 or 8A, 8 valence electrons except for helium. I'm going to list those here again. Helium, we told you before, has just the 2 valence electrons. And then we have neon, followed by argon, and krypton, and xenon, and then radon is actually radioactive, but all of these, I won't do them for all, but I will for neon. All of these have 8 valence electrons, 8 electrons on their outside energy level. And again, as we add a new energy level, we have more and more and more total electrons, but we'll never have more than 8 on the outside level. Helium has only 1 energy level, so that gets full at 2. Okay. Full outer shell, so very inactive. In fact, look at the word noble and kind of think of people who are so noble, high and mighty, and they say, you guys, you go do your own thing with whoever you want. We'll stay over here by ourselves. We're cool, we're noble, we don't need to do anything with you. And unless they are forced to under tremendous pressure, noble gases tend not to combine with other elements. That's why they're called noble gases. Do they have any use? Well, we don't see them in great amounts in the Earth's atmosphere, but there's a lot of these gases in outer space, so much of it has to be trapped by astronauts and pulled back in for use. Well, you've heard of helium balloons. You've heard of blimps. You've heard of neon signs. Okay? These all use the noble gases. Now, those signs are called neon signs, but they may actually use neon, argon, krypton, and xenon. Just different combinations of those gases will give us the different colors. Neon glows a nice bright red, and combining certain amounts of other gases with neon, the noble gases, we might see different colors. And that's why we have the neon signs that we might see around the cities at night. All right, but the noble gases, very, very inactive, do not combine with other elements because they have full outer shells. Ready? Now you look at many periodic tables, you see the bulk of it right up here, then these 2 rows on the bottom. You'll see a picture of it when we finish the notes here. Why? Well, there's a very scientific reason for that. They don't fit. In fact, I forget which page, but there's a page in one of these periodic table chapters, new textbook, that shows what the periodic table would look like. It'd be much wider than it really is if these 2 rows were in there. It'd be easier to show you what I'm talking about when I get to the page with the picture of the table on it. These are all transition metals as well. And so we have 68 total transition metals. Now, some of these are radioactive. The ones with atomic numbers above 84, they're radioactive. And some of them are actually made in nuclear facilities as well. Because they don't occur naturally, they're made in nuclear reactors. They're pulled out to keep groups also in line vertically. That helps line things up by the number of valence electrons and keep all of 3A together in group 3A and so on. Now you'll see there are 2 of them. Let's say you see one here that has 6 energy levels, and all of those are the lanthanide series. You'll see a picture of it in a moment. And the very bottom row is called the actinide series for, again, very sophisticated reasons I'll tell you about in just a moment here when I show you the picture. But these are the 2 bottom rows, and here's the main reason they're pulled and separated. It looks like there'd be some sophisticated scientific explanation for that. Well, it's because they don't fit and they want to save space. Okay, ready? All right, we're going to just see what this is. This is our last page, and we'll continue talking about electron dot notation a lot more in chapter 5, but it's right near the end of 4. Dot notation I've kind of drawn a little bit already, This shows the atom's valence electrons, the outside energy level of an atom. Remember how just a little while ago I was doing stuff like this, neon, and putting the 8 dots around. That's electron dot notation showing those valence electrons on the outside energy level. We're going to work a lot more with this in chapter 5, but just show you what that is, a definition right now. Here's a fancy word with a simple meaning, electronegativity, electron. Well, again, it seems like a big fancy word. Well, electrons are negative. All that means is an atom's ability to attract and hold electrons. Okay, an atom with high electronegativity, remember which kind of atom will add on more electrons? The nonmetals do, the ones on the right side. So which atoms have low electronegativity? The ones that won't add on electrons? That's going to be the metals over on the left side. So the metals have the low, and this really is the abbreviation for electronegativity, low En, and the nonmetals have high electronegativity because they will add and attract extra electrons. And here are just some examples, and we'll talk more about those in chapter 5. But you see, hydrogen has 1 valence electron, so do lithium and sodium. Beryllium and magnesium have 2 valence electrons. Boron and aluminum have 3, and so on and so on and so on. So they give you a little bit of example, and we'll talk more about that in chapter 5. Ready? Well, I thought I had the other periodic table up there, but I said we'd look at the example, so let's do that. Right there. And there we go. These are the lanthanide and the actinide series right here. The lanthanide series and the actinide series I told you about on the other page. Now follow this. Right here says 57 to 71. That means, look at group 3, it's also called 3B. All this right here, this series would fit right here. And that would stretch the periodic table out that much wider, way out here off the screen. Okay, change of color, and I'll show you that the actinide series, 89 through 103, that's going to go right there. And again, that would stretch all this out. So your periodic table would be, I can't even show you on the screen anymore because it would be way off the screen. But these are your lanthanide and your actinide series. This would be 3B, 4B, 5B. Now you look though, you got 1B is here, 11, and 2B with the 12 and the 2 there, and then 3B starts way over here. I wonder what's up with that. And really, all these 3 right here together make up 8B. So this is 6B with the 6 there, and 7B with the 7 there, and then 8, 9, and 10 are all 8B. And remember, the 1 valence electron for copper and silver and gold make that
Teachers,
1B.
pardon the interruption. There is a senior class Bible study.
Okay, we were done anyway, so I paused to let that announcement go through. And that's going to do it for notes 4B and 4C. Thank you once again.